So lecture 1-7, inductors. As with a lot of things in dynamic systems, and more specifically with electronics, there's sort of a dual relationship here. So we're going to really want to pay attention to that. Inductors are like the opposite of capacitors in a very specific sense. So let's define what they are. So a pure inductor is defined as an element in which flux linkage lambda, which is the integral of the voltage across it, across the inductor, is a monotonic function f of the current, I. In other words, the pure constitutive equation is that flux linkage lambda is equal to some monotonic function of the current. Okay? An ideal inductor, so this is like if you've got some component, it could be some weird function. As long as it's monotonic, we would say it's an inductor of some sort. An ideal inductor is the kind that we like because they're analytically easy to deal with and we can predict what they're going to do easily. Ideal inductor is such that this monotonic function is linear with slope called the inductance L. In other words, the constitutive equation is, make sure I don't give you the wrong one, lambda equals Li. So the flux linkage is proportional to the current. That's the ideal case. It's just like when you guys were talking in dynamics, I guess, about like springs, right? And they have Hooke's law. It's the force is proportional to the displacement from the equilibrium for the spring, and unstretched length for the spring. And the an ideal spring is just proportional, right? This K is the constant of proportionality. But real springs, like when you get to the ends, it gets nonlinear, right? And that's the same thing with inductors and with many of these components. We assume they're linear in this sense, but they're often only approximately so. It's good to keep that in mind. So the units of inductance are the SI derived unit Henry, H. Most inductors have inductance best represented by millihenry or microhenry, though. So once again, a henry is large. The elemental equation for an inductor is found by taking the time derivative of the constitutive equation. So just like last time, just like in the previous lecture on capacitors, we take the time derivative of the constitutive equation and we find ourselves with our elemental equation. So once again, I'm going to switch left and right here. So di dt is the time derivative of this side, so I'm going to divide L over. So di dt is equal to 1 over L times d lambda dt. So we said that the flux linkage is the integral of the voltage. So if you take the derivative, you're going to get the voltage back, right? So the time rate of change of the current through an inductor is proportional to the voltage across the inductor. So that's what an inductor is. That's what an ideal inductor is. Inductors store energy in a magnetic field. It's important to notice how inductors are, in a sense, opposite of capacitors. A capacitor's current is proportional to the time rate of change of its voltage. An inductor's voltage is proportional to the time rate of change of its current. So it's just sort of flipped, right? So they're like dual to each other was how we would say it. Inductors are usually made of wire coiled into a number of turns. The geometry of the coil determines its inductance L. So the number of turns around affects the inductance. The diameter of the wire affects the inductance. And then also the loop diameter affects the inductance. Inductors are used extensively in radio frequency or RF circuits. So like above 10 megahertz, really closer to a gigahertz is when you start to really be in RF radio frequency circuits, with which we won't discuss in this text. So we're not going to discuss RF specifically in this text. We're going to. I mean, we're not. What we're talking about isn't untrue of RF circuits, but RF circuits have a they have some complicated things that arise because of the wavelengths of the high frequency signals, and so you can get like the connectors and the lengths of the wires start to matter. So like the connectors cause reflections, it's called, and there's all kinds of stuff, power losses that come in RF circuits. So it's a lot more difficult to deal with. So we're not going to talk about that specifically. You can take classes on RF electronics, but we aren't going to talk about them specifically. However, they play an important role in AC to DC conversion, filtering, and transformers, all of which we will consider extensively. So we're going to use them, and also they can be used to describe the inductance of a motor coil as well. So there's inductance in motors that we'll also need to take into account. So they're important for us, even though we weren't going to talk about RF specifically. The circuit diagram for an inductor is shown in figure 1.5. So we said it's a coil. We draw it like a coil. And something that I didn't talk about in here, but which is also the case, is that these coils, and I'll draw a coil over here instead of using the symbol. These coils will often have some material inside the coil. So we'll put in a core, okay? So, I did say that. I skipped that sentence, I guess. So often a core material, such as iron or ferrite, is included by wrapping the wire around the core. It increases the inductance L. So if we put a core in there, so if we put an iron core or ferrite core, or sometimes we even put cores that don't actually increase the inductance. Like we'll put in epoxy. It's called potting it. And that's actually for mechanical strength. So if you just put this thing in the epoxy, it makes it mechanically strong, which may or may not be important for you in a specific application. But I've had to do that before, so it is something that does arise. But epoxy won't increase the inductance. So typically we try to do it with like an iron or ferrite core. You can buy them off the shelf, and people actually make inductors too themselves if they have like a very specific application that they want. But yeah, and it's cool because a lot of inductors, they just look like a coil. Like it's like not just like this abstract thing. Oh, it's like it's inside there. There's a coil. Like you can actually see the coil in a lot of cases. So it's pretty cool. Okay, so inductors. Not all of them. Sometimes they're coded. Okay, so any questions on inductors? So once again, derivative, right? Time derivative. So even more differential equations, okay? So if you've got a capacitor in your circuit or an inductor in your circuit, or both a capacitor and an inductor in your circuit, or multiple inductors or capacitors, you're going to get differential equations that are going to have higher and higher order, or you'll get, as Will tends to go towards, you'll get systems of first order differential equations, which is actually our preference. Okay, but we'll talk a lot more about that in the coming weeks.